To continue where we left off in the previous video of decoding or demystifying Eric Dollard's approach to the electric wave. And of course, we are using what I'm calling modified complex numbers to map out the equations that are commonly used in electronics. So previously we talked about impedance and I showed you how, and we talked about inductive reactance and capacitive reactance in the calculation of impedance. And as we saw, the inductive reactance is in the positive real, positive imaginary quadrant of the complex plane. And the capacitive reactance is in the positive real, negative imaginary quadrant of the complex plane. And the equation that we derived, the equation that I derived using modified complex numbers, combining both the inductive component and the capacitive component, looks like this. And so this would be a circuit that contains a resistor, a capacitor, and an inductor. And here you see that the resistor parameters for the resistor are on the forward diagonal, and the parameters for the reactance, both the inductive reactance and the capacitive reactance, are on the backward diagonal. But as you can see, the inductive reactance has a positive in the right corner and a negative in the left corner, and the capacitive reactance has a negative in the upper right corner and a positive in the lower left corner, and this is commonly referred to as the complex conjugate. Basically what it is a flip about the real axis. So the complex conjugate is a flip from positive to negative or from negative to positive about the real axis. So this is the imaginary axis, this is the real axis, this is the complex plane basically, and currently what we're talking about are the two quadrants in the positive real side of the complex plane. So now we're going to deal with the other component, the other very important component regarding electronics, and that is the admittance. And so the impedance and the admittance are related. So here what I'm showing you is that regarding impedance, you've got the inductive reactance and the capacitive reactance. And when we're talking about admittance, we're talking about the capacitive susceptance and the inductive susceptance. So we're replacing the term reactance, with the term susceptance. So what you see here, what we find here, is that the capacitive susceptance occupies the positive real, positive imaginary quadrant of the complex plane, and the inductive susceptance occupies the positive real, negative imaginary quadrant. So they're flipped. So in the case of impedance, the inductive reactance occupies the positive quadrant, and in admittance, in susceptance, when we're talking about susceptance, the capacitive susceptance occupies the positive quadrant of the complex plane. So from this picture, it's easy to see that the capacitive susceptance and the inductive susceptance are complex conjugates of each other. Just like the inductive reactance and capacitive reactance are complex conjugates of each other. But also Also, capacitive susceptance and capacitive reactance are complex conjugates of each other. And it's well known that susceptance and reactance are reciprocals of each other, they're inverses of each other, but they are also complex conjugates of each other, meaning that the capacitive susceptance occupies the positive real, positive imaginary quadrant of the complex plane, and the capacitive reactance occupies the positive real, negative imaginary quadrant of the complex plane. They are flipped about the real axis. And when something is flipped about the real axis, it is referred to as the complex conjugate. So before I continue, I just want to take a few steps back and define a few terms. These are terms that we've previously already used, but I thought it was important to just take a few steps back and make sure that we know what terms we're using here. And so R stands for resistance, and G will stand for conductance. And resistance is the inverse of or reciprocal of conductance, and conductance is the inverse of or reciprocal of resistance. And in terms of modified complex numbers, both resistance and conductance occupy the forward diagonal of the complex numbers, and they both have the positive sense. And so the resistance will be on the positive diagonal and conductance will be on the positive diagonal, and they will both have the positive sense. And so next we have reactance and susceptance. So X stands for reactance and B stands for susceptance. I'm not sure why, but they chose B. I didn't choose that. So B stands for susceptance, and reactance is the inverse of or reciprocal of susceptance, and vice versa. So susceptance is the reciprocal of reactance. And as we saw previously, the reactance occupies the backward diagonal, and it's got the positive in the upper corner and the negative in the lower corner, lower left corner. And susceptance occupies the backward diagonal as well, and as you will see, it is the complex conjugate of reactance. So it is the reciprocal of, and it is the complex conjugate of reactance, and so we will see that soon. But there's two here that we're not really going to deal with. There is one thing missing from this picture, and that is the receptance and the acceptance. Okay, and receptance has the letter H in Eric Dollard's paper, and acceptance has the letter S, and H is 1 over S and S is 1 over H. And just to show you the missing identity is assigned to the receptance and the acceptance parameters. And so this is, we're not going to deal with this right away. I will probably mention it because Eric Dollard does mention it in his paper. But these are the ones up here that we're going to be dealing with in this video. So getting back to this picture about capacitive susceptance and inductive susceptance, we see that now the capacitive susceptance is in the positive, real positive imaginary quadrant, and the inductive susceptance is in the complex conjugate quadrant of the complex plane. And so the equations map out as follows. The G, which is now conductance, is on the forward diagonal, and the capacitive susceptance is on the backward diagonal, and the positive component is in the upper right corner, and the negative component is in the lower left corner. And when you add these two together, you can combine them in one complex 1 2x2 matrix where G occupies the forward diagonal and the susceptance occupies the backward diagonal. And we can do the same. So here you see the inductive susceptance is in the complex conjugate of the capacitive susceptance. So what you're going to find is everything is the same, except that the inductive susceptance is on the backward diagonal. It's got negative in the upper right-hand corner and positive in the lower left corner, and you can combine them as follows. And so you can see that there's a nice analogy between the equation for admittance and the equation for impedance. And we can put them all together, and you can see them all together, and you can see the nice pattern. And so here you can see that in terms of impedance, the resistance is on the forward diagonal, and in terms of admittance, the conductance is on the forward diagonal. You can see that the resistance and the conductance are positive real numbers. And so here now you can see in the terms of impedance, the inductive reactance is on the backward diagonal, and it's positive here and negative here. And in terms of admittance, the conductance, the capacitive susceptance is on the backward diagonal, and it's positive here and negative here. In a similar manner, in terms of impedance, the capacitive reactance, so many terms to remember. The capacitive reactance is on the backward diagonal, and you've got a negative here and a positive here. And in terms of admittance, the inductive susceptance is on the backward diagonal, and it's negative here and positive here. And so, there are, a lot of similarities between the impedance and the admittance. Of course, the impedance and admittance are reciprocals of each other. The resistance and conductance are reciprocals of each other, and the reactance and the susceptance are reciprocals of each other. So this is a very nice pattern. Feel free to just pause this and study it for a bit. This is a very nice pattern. This is actually fairly easy to understand and to remember once you get used to the idea of two-dimensional numbers. So next we're just going to have a quick look at the equations for reactance and susceptance. And so here you've got the inductive reactance is equal to the inductance times 2 pi times the frequency. And of course the frequency is usually the frequency of the AC of the alternating current. And so in North America it's 60 hertz, 60 cycles per second, and in Europe it is, I think it's 50 hertz, 50 cycles per second. And so that is what you would plug in for the frequency term if you were doing this in terms of whatever standard that you're in, whether it's North American or European standard. And so I just want to point out something here regarding the 2 pi, because a lot of people have been asking me, why not just use tau? Well, tau is 2 pi. Okay, so there's sort of a fad or something, I don't know what to call it, but there's like a fad where people think it would be better if we, instead of having a symbol for pi, that we have a symbol for 2 pi. And I like this idea. Mike Goldman kind of presented this to me, and I did a little research, and it does seem to be a thing. But here's the problem I have with this. To tau or not to tau, that is the question. I think it would be a good idea. It would have been a good idea to do this 100 years ago. But now everyone is used to 2 pi. They know what 2 pi means. They don't know what tau means. So if I wrote these equations without any context, down here I would have to say tau equals 2 pi. I would have to write that down, and which would be fine. Okay, this actually looks real pretty. I like it. Okay, I like it. But because, you know, I want to be able to talk to people that have studied this stuff that don't know what tau is. And so I'm going to continue to write 2 pi, even though I think it would be much prettier to write tau for 2 pi. Everyone knows what 2 pi is. When I see 2 pi f, I know I'm talking about angular frequency. And so I like to put, you know, I'm trying to be more clear. I'm trying to not obscure things with symbols. And so I personally think it's better to put the 2 pi in the equation. That way I can see it. I know it's there. I know what it is. And guess what? Everyone else knows what it is. So that's my spiel on that. So the inductive reactance has this equation. The capacitive reactance is the reciprocal of this. Of course, here you're plugging in the inductance of the component that you have your inductor, and here you're plugging in the capacitance of your capacitor. And so in terms of susceptance, it is it's reversed. So the capacitive susceptance is written like this. So this is capacitance times 2 pi times frequency, and the inductive susceptance is the reciprocal equation, only you plug in the inductance instead of the capacitance. And so you can put those directly into the equation. So instead of writing inductive reactance, you can plug the equations in. And this is what they look like. So if you want to calculate impedance, you plug this equation in here, you plug in your resistor parameter in here, and you get the impedance. And same with the admittance. You could plug in the capacitive the susceptance into the backward diagonal and put conductance on the forward diagonal, and you've got the admittance. And then of course you've got the reciprocals. So you've got you plug in the reciprocals when you want when you have a capacitor. When you want to calculate impedance and you have a capacitor, you use this equation. And when you want to calculate admittance and you have an inductor, you use this equation. And so, you know, so this might be actually easier for someone to remember because it's got the equation for the reactance and the equation for the susceptance built into the matrix. So next we're going to see what happens when you multiply impedance by admittance. Okay, so this is going to be an example of how to multiply together 2 by 2 matrices. So up to this point, we've only been adding matrices together. We build one matrix for each component. So in this slide here, we've got a resistor and an inductor, or a resistor and a capacitor, and you can add them together to combine them into one matrix. But here we're going to multiply the impedance by the admittance, and we're going to use matrix multiplication. So this is the case. In this case, we're gonna do the case of the inductance. And so we've got reactive inductance on the backward diagonal, and we got inductive reactance on the backward diagonal, and inductive susceptance on the backward diagonal. And knowing that the inductive reactance is positive in the upper corner. So if we look at this slide here, we see that the inductive reactance is positive in the upper right corner and negative in the lower left corner. And similarly, the inductive susceptance is negative in the upper right corner and positive. Let's see if we can find that here. So the inductive susceptance is negative in the upper right corner and positive in the lower left corner. So just by looking at this, I can tell that this is the case of the inductance. And so I'm not going to write the little subscript L, just to make the code look a little cleaner. And so what you do, I'll show you how I multiply matrices together. What I do is, so what you do is you take a column from the right hand side and you turn it into a row. You bring it over here. This is how I do it. So I'm just bringing it here so I can see it clearly over here. And what we're going to do is we're going to generate the first column of the output array, of the output 2x2 matrix. And so clearly you can see that we have R times G plus X times B goes in the upper left corner. And then we go down and we multiply this by this. So we've got R times B, positive R times B, which I put here, and negative X times G, which I put here, and I write it as RB minus XG. So now we're going to do the same thing. We're going to take this column here, and we're going to write it up here. I only do that because I visually need to see it. I can do it in my head, but this is how I do it in my head. I bring this over here, and then now I'm going to calculate the right-hand column of my output matrix. And so here you can see it is minus R times minus B, which is minus RB. And then you've got X times G, which would be positive. So in this corner, you've got positive XG minus RB. And now we're going to do the bottom one here. We've got R times G, positive R times G, and minus X times minus B, which is positive XB, which we write here. Okay, so now we've got both columns, and this is what it looks like. So you can see that the RG plus XB is on the forward diagonal, and we've got XG minus RB over here, and we've got RB minus XG over here. These are, inverses of each other. And so we can group them more like this. So this actually makes more sense in terms of complex numbers. When you take a complex number and multiply it by a complex number, you end up with a complex number. And in a complex number, the imaginary component, the backward diagonal, has opposite sense. So the forward diagonal has the same sense, and the backward diagonal has opposite sense. So what I did here was I grouped these just to show. So I rearranged this to be minus XG minus RB, which is positive RB minus XG. But when you see it this way, you can clearly see that the component in brackets is the same, and you have positive here and negative here. And so you can clearly see that this is a complex number. So when you multiply two complex numbers together, you get another well-composed complex number. So this turns out to be the it's equivalent to the known equation of Oliver Heaviside. Okay, this equation, which I've seen in the works of Eric Dollard before, this is, in fact, what I've derived right here is exactly this equation here, where you've got, R times G plus X times B plus J, which is the imaginary identity that Eric Dollard uses, X G minus RB. So this is exactly what I have, XG minus RB. And this is the positive J because in modified complex numbers, positive J, which I call positive I, has a positive in the upper right corner and a negative in the lower left corner. And this is exactly what I have derived here, is an equation with positive in the upper right corner and negative in the lower left corner. And this is exactly the equation that Eric Dollard attributes to Oliver Heaviside. Now, I have not been able to find a reference for this written by Oliver Heaviside. I've seen Eric Dollard present this, but I've never seen anything from Oliver Heaviside. I haven't been able to find it. So if anyone out there has a reference to this equation written by Oliver Heaviside, maybe it's in one of his books, maybe it's in one of his papers, I would really like to get this reference, because if I do write a paper about this, I want to be able to reference this equation. And so here Eric Dollard is multiplying z times y and deriving, basically saying that this is Oliver Heaviside's equation, which I have reproduced right here using modified complex numbers. So this is really interesting. This is really a nice application of modified complex numbers. It's, quite simple to understand. And, all you have to know how to do is multiply and add. And all of the parameters that go into these two-dimensional complex numbers are real imponderable numbers. These are real numbers. These are actual numbers. I don't know if I should call them real numbers. I guess I could call them actual numbers. They are real numbers that you plug into the equation, and you never ever have to write I. But if you want to, you can simplify it. You can write it like this as an expression to make it look cleaner on a piece of paper. Obviously, two-dimensional matrices aren't as convenient to write as equations written on one line. So it's still nice to be able to write this, but when you write this, what I want you to do is I want you to see in your head, I want you to see this. It's very important that the backward diagonal has a positive here and a negative here, especially when you're doing multiplication. This equation would not work out if that wasn't the case for these two matrices here. And so this is the complete expression for the impedance times the admittance. Okay, there's nothing hidden, there's nothing missing, it is all here. And there's no, mystical creature called the imaginary number I or j anywhere near this expression here. And so what Eric Dollard does is he associates the real component with a power factor, and this component here with the induction factor. And as I said before, this equation, what I did here was done in terms of inductance. Okay, and so he also says, so this equation, the real and imaginary component are the power factor and the inductance factor, but it is, however, or it is also, the real component represents the continuous wave in this expression, and the backward diagonal represents the transient wave. So he says where xg and rb are the magnetic and dielectric time constants, respectively, in Nepers per radian. And so thus this equation serves as a starting point for the study of transients. So this expression here, he claims, is what gets us one step closer to understanding the transient components of the waves. But what about the capacitive factor? What about the capacitive factor? Well, I'm not going to do the multiplication. I'm going to show you the results of the multiplication, and intuitively, so here is the equation z times y with the inductive reactance and the inductive susceptance, and here is the equation in terms of capacitance, and this is the capacitive reactance, and this is the capacitive susceptance. And you can see that the capacitive reactance is the complex conjugate of the inductive reactance, and the capacitive susceptance is also the complex conjugate of the inductive susceptance. And so intuitively, you would expect that the result of this multiplication should give us the complex conjugate of the inductive result that we got here by multiplying impedance by admittance. And in fact, this turns out to be the case. So I will leave it as an exercise to you guys to do the multiplication, multiply these two matrices together using the method I showed you, previously, or whatever method you've learned if you watch the videos that I showed you before on multiplying matrices together. And so this is in terms of capacitance, so what does he call it? The capacitance factor, not the induction factor, but the capacity factor, when you multiply the impedance by the admittance, is this expression here, and it is the complex conjugate of the inductance version. And so that is where I'm going to leave this today. These are the most important points that I was able to extract from Eric Dollard's paper, okay, from this paper here. There's a lot more in here. Maybe I will also make a video of basically trying to show how I came to these conclusions about these complex numbers. But this is really where I want to get from my perspective. I've seen this equation before, and I knew it had to do with complex numbers, but I really wanted to see how it mapped out, and I think that I've done a good job of mapping it out. This is exactly what that equation looks like in complex 2x2 matrix form in modified complex numbers. And so this is very useful. I think this can be applied. Let me just go to the final one here. Right, so this looks nice here. So we've got the we've got the real component on the forward diagonal. They are both positive. We've got the imaginary component on the backward diagonal, and in terms of inductance, it's positive here and negative here, and in terms of capacitance, it's negative here and positive here. And so this is really, I think these are all the tools you would need to be able to solve any problem in a circuit. I can't see what else you would need to be able to do what people normally do when they are sorting out a circuit and trying to find out what components to use, etc. And so really what I've developed for you here is a nice tool that may or may not be easier for you to understand. If you learned it the old way, this may be more confusing to you, but if you have never done this before, then this might actually help you to sort it out. As I showed you before, okay, there's a nice pattern here that you would have to remember, but once you remember it, then you would be able to use this, to solve problems. And so I'm going to leave it at that, and this may or may not be the last video I do on this paper. I really don't think it's important that I torture you with the details of how I extracted this information from Eric Dollard's paper, but I may do it for fun someday, but I think there's lots of other things I need to do. So this is it. This is how you apply modified complex numbers to electronics and in the development of an electronic circuit. So thank you very much, and I hope you're having a great day.